Welcome to the Walton Pi. Today we're going to be talking about what it means for something to be a field. So the mathematical definition says that a field is a commutative ring with identity not equal to 0, where every non-zero element has a multiplicative inverse. Now, that's a lot of stuff. Let's break it down bit by bit. So in other words, a field is any set of elements together with two operations, addition and multiplication, such that we have the following properties. First, we have a plus b plus c is a plus b plus c, a plus 0 is 0 plus a is a plus negative a is negative a plus a is 0, and then a plus b is b plus a. That makes this a group. A times b times c is a times b times c, a times 1 is 1 times a is a, and a times b is b times a. That makes this a commutative ring. Okay, identity not equal to 0 tells us 1 is not 0. And then we also have this other condition, a multiplicative inverse. So that means that if a is non-zero, then there's an element which we're going to call a inverse, such that a times a inverse is a inverse times a, which is 1. So all of that together means that this is a field. So if all of these properties check out, that means that this is in fact a field. So what are some examples? So you've already seen quite a few already in various math classes that you've probably taken. The set of all real numbers, that's a field. We have addition, subtraction, multiplication, and we can divide by anything that's not 0. So that is an example of a field. We also have the set of all complex numbers. We have the set of all rational numbers. That's actually a field. If you're not entirely seeing that, go ahead and try it. See if all of those properties that we showed earlier check out. But then we also have the set of all integers. This is not a field since we don't have multiplicative inverses. For example, for the element 2, to have 2 times something equal 1, which is our multiplicative identity, we would need that thing to be 1/2, but 1/2 is not an integer. So that's why the integers are not a field. They are a commutative ring with identity not equal to 0, but they don't have the multiplicative inverses. There's also examples of finite fields. All those fields that I just listed, those are infinite fields. But some finite fields are things like z mod pz, where p is a prime number. That's going to be a field. But we can also have fields of non-prime order. Now these are a little bit trickier, and these are not nearly as intuitive, but I'm going to provide an example of one, and then you can go ahead and check that this is in fact a field. And later on, I'll probably make a video on how to make these finite fields of non-prime order. But right now, I'm just going to give this very simple example and leave it at that. So this set of 4 matrices in entries in Z mod 2, so 0 and 1, where 1 plus 1 is 0, that is going to be a field. So we have the 0 matrix, the identity matrix, the matrix A, which is 0, 1, 1, 1, and then A squared, which is also A plus I, and is also actually A inverse. This is 1, 1, 1, 0. Okay? Go ahead, check that all of this works out, that this has all the properties it needs to, but this is actually a field of a non-prime order. So, I hope that this was helpful in understanding what fields are. If it did, please like and subscribe. It really helps me out. If there's other things that you would like to see me make a video on, please leave that in the comment section down below. I hope you have a great rest of your day, and good luck with all of your math.